Last week, we talked about the phenomenon of quantum entanglement, discussed the Einstein-Podolsky-Rosen paradox, and also considered an experiment to test Bell's inequalities. We found that the description were hidden parameters of the microcosm phenomena turns out to be untenable since Bell inequalities are violated, and we must use the quantum theory. It should be reminded that the so-called EPR pairs, or Bell states, played a key role both in Einstein-Podolsky-Rosen paradox and in the Bell's inequalities tests. In one of the lessons, we mentioned that pairs of qubits prepared in one of the 4 Bell states are a very important resource for many interesting practical applications. However, before we will be convinced about it, we will need to consider the elements of quantum logic, because these are the exact tools to work with qubits. First, we go back in time a bit and recall logical elements which used for classical computations and only then proceed to the quantum case. The analogies obtained from this will be helpful because they will allow us to better understand the differences between classical and quantum calculations. Nowadays, there are a large number of various computers and computing devices, from the simplest one that we could find in our everyday life to huge supercomputers used in science and industry. However, despite all differences in the physical implementation and in the purpose of these devices, from the point of view of the computation theory, the operation principle of any of them can be described using the so-called Turing machine. In most strict terms, this statement is called Church-Turing thesis, according to which a computational problem can be solved on some physical realizable computer only if it can be solved on simple abstract machine called the Turing machine. The slide you see now shows a schematic of a Turing machine. It consists of a control device that plays the role of the microprocessor. It controls the position and state of the head. The head reads and writes information on the endless tape, which divided into cells and played the role of memory. Each cell can contain bits of information, there is zeros and ones. Thus, sequences of cells form the code words, and some cells contain the character B, which denotes a space and with which the code words are separated. In addition, the beginning is sometimes indicated on the tape as it is done in the picture with the yellow arrow. At each step of the Turing machine separation occurs sequential execution of program lines, which arrive at the control device. The reading head transmits the value of current character on the tape. Each symbol is converted in the control device depending on the code of the program line and then written back to the tape. Then a transition to the next current or previous tape symbol occurs according to the result and at the command line code. The main feature and advantage of the abstract Turing machine is its comparative simplicity. However, in practice, an equivalent circuit model, or in other words, switching circuits, often used as equivalent to the Turing machine. Unlike the Turing machine, the circuit model is no longer infinite. This model is especially good and clear when we want to compare classical and quantum logical operations. This slide shows such a circuit. It converts 4 bits as the input, that is A1, A2, A3, and A4, into 3 bits at the output, B1, B2, B3. This transformation is performed using 4 logical elements, G1, G2, G3, and G4, represented as green rectangles. Horizontal lines indicate the wires through which the bit values are passed to the logic gates. The action of each logical element can be represented as some function that translates the bits at the input of this element into a set of bits and its output. It should be noted that all transformations occur from the left to right, so firstly, element G1 transforms the bits A1 and A2, and only then the result passed through the element G2, and so on. Often, for a convenience and consideration of switching circuits, we could introduce a time scale. Various time points of this scale are indicated by vertical lines. Moreover, we had identified time points before and after transformation carried out by logical elements. So, at time t0, we have 4 bits A1, A2, A3, and A4, which are entered into the switching circuit, and by the time T1, we still have bits A3, A4, and also converted bits A1 with tilde and A2 with tilde, resulting from a logical operation on the element G1. Finally, at the time point T4, we have the values of bits B1, B2, and B3, which are the result of the conversion using the switching circuit. It should be noted that the number of bits at the input and at the output of the switching circuit may differ, which is determined by the type of logic elements used. For example, the input element G3 have 2 bits and their input at only 1 bit of information after transformation. The reverse situation may also arise in classical computation. Let's now consider the most commonly used logic gates. Many of these elements are likely to be known to you from school. For the convenience of describing their actions, we present the so-called truth tables, in which all possible values of bits at the input of the element are linearly entered, as well as the results obtained for these values at the output of the element. The third logical element that we consider as the NOT element, which is also called logical negation. The slide shows its schematic representation in the form of a triangle with a circle, and as well as truth table. The NOT element has 1 input bit and 1 output bit. This element replaces the value of the bit A at the input with the opposite. That is, its action can be described using the modulo 2 addition of A bit value with a unit. Recall that when adding modulo 2, we must first simply add the numbers and then divide the result by 2. The remainder after dividing will be the result of addition modulo 2. When we summarize 2-bit values, we get 0 when both bits are equal, that is, when each bit is 0 or when each bit is 1, and we get 1 in all other cases. That is, when we add 2-bit values, we get 0 when both bits are equal, and we get 1 in all other cases. The next logical element that we consider is the AND element. The operation that that element performs is also called conjunction or logical multiplication. It is schematically represented using a semicircle. Unlike the NOT element, the AND element already has 2 input bits, which we denoted as A and B. The result, the C bit, is a simple multiplication of A bit by B bit. That is, if at least one of the input bits is 0, then the C bit will be also 0. Bit C is equal to 1 only in the case when both bit A and bit B are equal to 1. Recall that in the Boolean algebra, 1 is often compared with the concept of truth and the concept of false with 0. It can be said that the result of the logical element AND will be true only when bits A and bit B are true. If at least one of them is false, then the result will also be false. Mnemonically, it is usually remembered as both of them. In order for an element C to be true, both element A and element B must be true. Now, let's consider the OR element. It is also called a disjunction. It is schematically depicted as a crescent. Like the AND element, it has 2 bits A at the input and 1 bit C at the output. The result of the OR operation can be represented in different ways. For example, it can be represented as the largest value among the bits A and B. Thus, if bits A and B are 0, then bit C will be equal to 0, and in all other cases, bit C will be equal to 1. Bit C can also be represented as the difference between the sum of bits A and B and their product. The mnemonic action of the element OR is remembered as either this or that or both. That is, either the element A is true or the element B is true, or both elements A and B are true, and then the resulting element C also turns out to be true. Another element that we will consider is the XOR element, exclusive OR. It is schematically represented as an arc and a crescent. Like the previously considered AND and OR elements, it has 2 bits A and B at the input and 1 bit at the output. Its action can be represented as the difference of the largest and smallest values of bits A and B, or as modulo 2 of these bits. Thus, the bit C is 0 in cases where bits A and B are equal and equal to 1, when their values differ. The mnemonic effect of the XOR element is remembered as either one or the other, but not both at once. In conclusion, let us consider the action of 2 more logical elements characteristic of classical calculations. These are the elements erase and fanout. The erase element deletes the A bit on which it acts from the computer's memory. It is schematically depicted as a cross. The fanout element is represented as a branching wire and creates a copy of bit A at its input. We emphasize that these 2 elements are typical for classical ones, especially fanout elements. This is due to the fact that in the quantum case, it is no longer possible ways to create a copy of the qubit, which we will soon have to talk about. Of course, there are other logical elements, and we will define them as necessary. That's all. Thanks for your attention.